Okay, so there's a lab this week. We haven't had a lab for a while. But, so Jay's back. Right. And I sent out a message that should help regarding the write-ups for second experiment. Okay. I think I've seen all groups except one. Tomorrow? Okay. Oh, so I can put that down right now. That's 7:30? 7:30. Okay. Okay, so we're talking about waves, and we're focusing on a string. That's the sort of the easiest, can easily considered to be the easiest system, most picturesque transverse waves on a string under tension. And next we want to address this important concept of normal modes. Now I should tell you right from the beginning that normal modes here are just going to be what we call standing waves. So you might say, well, why are you calling them normal? What's the big deal? Well, I want to explain the big deal to you. So let's do an aside here, and we're going to look at not a wave system, but a coupled system of oscillators. And here's the prototype case that people do in mechanics. You guys see this? This is the simplest case. You have two equal masses, two equal springs. So these are identical oscillators, and they're coupled with this spring here. And you usually allow this could be anything. And the most interesting behavior occurs when S prime here is substantially weaker than this. Right? Now I think I demonstrated this for you. Remember this apparatus? I think I brought it out early. So now we want to look at it a little bit more carefully. And this is a linear system. This is mathematically identical to this for small amplitudes. This is actually nonlinear because pendulums are nonlinear. Okay? And there can be, with arbitrary initial conditions here, you can get what looks to be like sort of complicated behavior. But we have a name. You can see there's a kind of partial beating of energy. Some of the energy is going back and forth. And that's what characterizes this coupled oscillator system when you have weak coupling. So let me do a demonstration that I probably did for you weeks ago. I'm going to pull this one aside and then let them both go from rest, okay? Now you can see this one starts to drive that one, and then it's dramatic behavior. There's a moment here when, right about there, when it looks like all of the energy has gone into this one. And a lot of people think that's the case. But if you scrutinize the math, you'll see that you can only get complete energy transfer in the limit of zero coupling, which is, then you don't have a coupled oscillator system in that case. But it does look like we're getting it all. So people usually just say it, okay? So what's happening here is it just keeps beating back and forth, this energy. How do we explain this? Well, I know of two explanations. One is sort of qualitative and not real rigorous, but the rigorous one involves normal modes. And here's the idea. Every system of coupled oscillators is going to possess modes where there's a single frequency, right? Is there a single frequency here? Is this a normal mode? No, you see there's a fast frequency here, then there's a frequency with which energy goes back and forth. It's not a normal mode. You can probably guess what the normal modes are. I might have talked briefly about this weeks ago. Any guesses? Yeah, you let them go with the same amplitude. This is just going to keep doing that, right? The surprise is, for nonlinear oscillators, it doesn't happen. That's an instability. I think I might have mentioned this. Does this ring a bell? It seems like a long time ago, doesn't it? Yeah, and when I was at my previous university, we did a literature search. Nobody had commented, so we published a paper on this. And we backed it up with computer analytical work and computer simulations. Easy. So it's called a parametric instability. But at low amplitudes here, this is a nice normal mode. It has one frequency, and it looks boring, right? What's the other one? Well, so once you've seen that one, you know the other one. It's going to be 180 degrees out of phase, right? So that's the other normal mode. And the big deal about normal modes is, by superposing this motion and this motion, which is just adding them together, we can represent any motion of the system for small amplitudes in this case. So let me diagram that for you. We started off with this initial condition. This is like the top view, and I'm pulling this one aside and I'm releasing it from rest. So I'm going to represent it like that, okay? Okay? All right? Now, the claim here is that normal modes, by superposing them, you can represent any motion of the system. And what we want to do here is recognize, guys, it always gets in the way. So here's our initial state. I can think of this as this mode initially. So what happens when I add these two? I'm doubling it. What happens when I add these two?
Zero.
Yeah. So this is actually the normal mode content. Each mode, each of the two normal modes is equally excited here. And it's hard to see that, but mathematically I think it's pretty clear, right? So the claim is that this represents any motion. And in particular, it will describe, this will explain why we get beating. Because another thing you note about the normal modes is their amplitudes stay constant. The amplitude of this mode doesn't care about that. They're uncoupled. And again, that's hard to see here, but I think it's reasonable. And when we're going to prove it in the case of a string, we will actually prove it. Whatever the initial content of energy in here and energy in here, that energy won't change in time. This mode is uncoupled from this mode, and vice versa. So what's going to happen as time goes on here? What's the frequency of this mode compared to the frequency of this mode? Can you see that? This mode is equivalent to a single pendulum of this length right here, right? Going down to the bottom. So this mode is equivalent to a single pendulum of this length. What about this mode?
Shorter.
Oh, it's shorter. That's the right answer. You don't want to solve for it. I did. I have solved for it. But somewhere in between here is the effective length. So this one has a little bit greater frequency than this one. So as we go on in time, this going like this at its frequency, this one going like this at a slightly greater frequency, there's going to be a time at which what happens, at some later time. What's going to happen?
Yeah, two down.
We can put, it doesn't matter here because we're assuming the weak coupling case. I can write this. You want me to put this down? It doesn't matter. But the important thing here is that this one, what is gaining a little bit ahead in phase, it will eventually be like this. And now what happens when we add these two together? Something's not right here.
It should be
Oh,
two down.
God, this is not right. So let's do it this way. Sorry. Oh, this is right. So the point here is that because there's a little frequency difference here, this one's going to gain in phase compared to this one. And eventually, instead of this being 180 degrees out of phase, this is going to be 180 degrees out of phase. And then we get this. So we get this energy transfer, this nearly complete energy transfer to there. And now, as time goes on again, eventually there's going to be another time. If you wait about the same amount of time, now it's going to be back here. So this is you can see one usefulness for the normal modes right here. It explains this beating phenomenon for weakly coupled oscillators.
You said that if the coupling goes to zero, then it's.
Yeah, I probably shouldn't have told you guys that. Okay, now I'm regretting. But it turned.
Wilberforce oscillator.
This happens for any system of coupled oscillators. It happens for the Wilberforce too, and that's even weaker coupling than this. The Wilberforce Oscillator, which Michael knows well, okay, because he's doing his joint thesis on it, it's where you have a mass on a spring that does this, and it's coupled to the torsional motion. And those two frequencies, the uncoupled frequencies, are selected to be the same. So you get this really very slow beating. And it looks like there are points when there is complete 100% energy transfer. But if you look carefully at the theory, if you look at some graphs in some mechanics books, typically this is done in mechanics books, it's not 100%, but it's close for weak coupling. The weaker the coupling, the more complete the energy transfer. Okay, and now I've learned, I'm not going to say it anymore in a class. It's just just one of these things that it's probably best just not to say and just leave it. Okay, any other questions or comments? So what we're going to do now is look at the normal modes for a string. We're going to choose a fixed string. And these are going to end up being the standing waves, as you'll see, which you'd probably expect. But they do have this greater significance. And we will prove that they by superposing, in this case we superpose the two possible modes, we can represent any motion of the system. We just have to put in the initial conditions, like this. The same thing's going to happen for the string, except there are an infinite number of normal modes now. Essentially an infinite number. So let's see how this works. Incidentally, the whole idea of normal modes we're neglecting, there's no drive and no dissipation. These are three motions of the system. Okay? So it's not a big leap to put in drive and dissipation. The normal modes will correspond to resonances, as you know, like that. But the issue to be addressed here with the normal modes is for an undriven, undamped system. And we ask to have the same frequency. So here's our system of interest. It's a fixed string, length L. The left end will be x equals 0, the right end x equal L. We know that, even though we didn't prove it, that the general solution here has to be some right traveling wave plus some left traveling wave. Because we have the wave equation, no dissipation, no drive. So this will describe the motion. Let's impose the boundary conditions. First, you always go to the easy one first, x equals 0. When I set x equals to 0, I set this all equal to 0. I cancel the e to the I omega t, and I find that these two amplitudes, which are in general complex, as you know, they have to sum to be 0. So we can eliminate b right now. We can put b equals minus a there. And then I've skipped a few steps here. Because we have a here with a minus sign, I can factor out an e to the I omega t, but we have an e to the minus ikx and plus ikx. And the minus is on the left side, so we get a minus 2i times the sine of x. We're using that standard identity, okay, for exponentials, for the sine. So that's how we do that a lot in this class. This is how we get this right here. And the way we think of this is just some complex amplitude here. Which will be ultimately specified by initial conditions. What about the other boundary condition? Well, at x equals L, we have to get 0. So the only way that's going to happen, and we can't have a 0 amplitude because then we don't have any disturbance at all. There's nothing going on. We've got to have KL has to be an integral multiple of pi. Okay? So what sits in here, the most general solution is, 0 pi, 1 pi, 180 degrees, right? Etc. So we get what's called we get this discrete modes here. We only have solutions for a discrete spectrum of wave numbers here. It has to be n pi. We rule out the case n equals 0 because that's just no response. That's 0 amplitude. That's the only way you can solve. For k equals 0 is infinite wavelength, and we have to satisfy the boundary conditions. So that's just this equilibrium, the string at rest. So the wave number here, we can easily solve for this, and it's n pi over k. And that's going to imply, you can set this equal to 2 pi over the wavelength and find the wavelengths. We can find the frequencies because omega is equal to ck. So the frequency spectrum has to be c times this. I can divide by 2 pi to get the normal, instead of the angular frequency, the normal frequency in hertz. So usually we think of it like this. This is the possible frequency spectrum of these normal modes. The disturbances of the string where there's just one frequency, like this. The really nice looking simple cases, like this one and this one. So what does the waveform look like? This is our discrete frequencies. What does the waveform look like? Well, it's not going to surprise you. We write this. Now, I kind of regret doing this. If you want to make this look easier to understand, replace this A with a C here. It's going to be some complex number, and it can vary, of course, from one mode to the next, right? So we put an N on it. So think of this as a capital C in some complex amplitude. This is what all this is irrelevant, okay? We can easily redefine, or so some people say is they absorb this into this constant here because constant here. So we get this is some complex amplitude. It will have a real and an imaginary part. The minus sign is just for convenience. You'll see why. So it'll turn into a plus sign. It's just for convenience. I know it looks a little confusing. But take this, substitute it into here, and then take the real part. Remember, ultimately, it's implied here that we take the real part, or the imaginary part. We'll take the real part to get the actual displacement of the string, right? So when I take this and substitute it into here, you can see there's going to be, where these are real numbers, A and B are real numbers, I'm going to get a cosine omega nt multiplying the A, right? And I'm going to get a sine omega t multiplying the B. And because of the i's here, to make this a plus, you got to put a minus sign there. That's all, just to make it look clean here. Okay, so that's our actual wave. You can see that it's a sinusoid in space, and it meets the boundary conditions. You know what it's going to look like. We can jump ahead. Because of this right here, what these look like is just this. You saw these waves on it. I did them on a spring, right? And we saw, yeah, that's. I think for the torsional wave apparatus, I don't know if we did, I can't remember what boundary conditions we used. It's kind of difficult there. But the spring, just a simple long spring is a good example of this. There's a half wavelength. That's the sine of the k1x. The sine of 2k of k2x. K2 is just twice k1. It's just going to be one full wavelength. So we get an integral number of half wavelengths here. That's what's emerging. Oops. That's what comes from right here because of the discretization of k. Now, how do we get A and B? How do we get these A and B coefficients? We have two undetermined constants there. Those are ultimately, if you want to, some people just stop right here. Okay, we know the normal modes, but to completely exhibit this, we want to be able to show that we can set these constants to match any initial condition. So these are determined by initial conditions. And the other thing you need to know is, to get the general solution, we have to superpose these for all values of n. So the claim, and we're going to prove it, is that the I'm jumping ahead. Excuse me. Let's forget what I just said. These are going to be set by initial conditions, and we'll show how that works, okay? Let's exhibit just the modes here. These YNs are called the normal modes. In acoustics, we usually just call them standing waves, but we understand that they are the normal modes. In quantum mechanics, they call them eigenfunctions. Okay, sometimes people use that for classical waves too. We have normal modes and we have normal mode frequencies. That's the spectrum. It's very simple in this case. Again, you know, we can get the K. Through K, we can get the frequency. And from that, we can get the wavelength, or you can get the wavelength directly. There's a number of ways of doing it. It looks like this. And I know this looks probably confusing, but what this is saying is that we have to have an integral number, as I mentioned before, an integral number of half wavelengths. So this is what people usually have in mind when you have fixed boundary conditions. And you know what's going to happen if it's free, and we'll actually demonstrate. I'll do a demonstration of that shortly. Or you can have mixed boundary conditions. You can have fixed free. And right now, I think all of you know what the modes are going to look like, right? For example, what's for fixed free? What's it going to look like? I have a string here, and it's fixed here. There's no mystery here. The lowest frequency mode is going to look like this, and then half a cycle later, it'll be a quarter wavelength, right? And the next one, we will add a node here, so it's going to have to look like this. It's going to look something like this. So there's 1, 2, 3 quarter wavelengths inside there, and etc. Now, I demonstrated for you, I didn't bring it out because I demonstrated it before, the long spring where I was driving the end with a small, effectively fixed displacement drive. And you saw it resonate, right? And we went to this one too. It's kind of high frequency. Incidentally, an important point here, and well, it's right down here. In this case, and also in the free case, the standing wave modes here, which are the normal modes, are harmonically related. This one is twice the frequency of this. This one is 3 times the frequency. We call those harmonics because of they're related by just an integer factor here. I demonstrated this for you. When the torsional wave apparatus, we did something, okay. But this is one that many people have not seen. In fact, a professor just before class thought this was new. It's obviously not. You can see the paint's chipped here. But he'd never seen this before. It's just been in the demo room. I usually don't bring it out except for this class, which I don't teach very often, right? So what this is, let me turn on the lights. And it's good for you to see this because these are not transverse waves. What are they? Longitudinal. And that's what sound is. Sound is compressions and expansions, moving this way or that way. So it's the same idea. And in this case, there's the wave equation. As long as the wavelength is small compared to this lattice spacing here, you're going to get discrete. You know, this is not a continuum, right? Because we have these. Ultimately, you know, this has 2 degrees of freedom because you need to specify this and this. This is not infinite degrees of freedom here. 18, 19, 20, 21. Yeah, they probably chose an odd number so that some of these will be nodes. It says 21 modes, so it's not quite infinite. That was a joke. Okay, but they're going to be standing waves here, and those are the normal modes of the system. Okay, now it's best to demonstrate this free rather than fixed, but you know it's going to be very similar, right? What is the fundamental mode, the lowest frequency mode, which we call the fundamental mode usually? This is very common language. We've already used it a lot. You're probably using it in the lab. Everybody uses that.
They're all passing it.
No, that's the next mode up. Here, what about this? The lowest frequency mode. Yeah, so what we got there is for free, it's going to be a half wavelength. Looks like this, then half a cycle later. It didn't. Well, that's close enough. Okay? So you'll notice here the ends are actually 180 degrees out of phase, aren't they? Yeah. And then in between there's a transient here, and let me see, I'm trying not to drive this too much. The node is right in the center, right? Which should be that one. Yeah, it's moving a little bit. It's not exactly uniform, the lattice. Okay? But please note, okay, here's what's happening. It's easy to see transverse waves, right? Because they're transverse to the lattice. These are longitudinal. It's a little bit harder to see. But we plot them the same way. We plot, for a transverse apparatus, this is actually what you would see, okay? For a longitudinal apparatus like this, there's a little bit of a leap there. We're representing this motion perpendicular to the lattice in the graph here. But, it's not a big deal, but there is a distinction. What's the next mode up look like? Now these are going to be, this is what James was thinking, now these are going to be in phase here, and we're going to have one wavelength. I don't know if I can draw it here. Let me try to draw it like, and half a cycle later it'll look like this. So you can see this is a half wavelength, this is a quarter, well, it's one wavelength. You can see that it's one wavelength. So now they're going to be in phase. So I got to go like this and drive at the right frequency, twice the frequency as before. This is the low frequency. Hold on a second, I just have to think. Let's try to do it at twice the frequency. Now, we've added a node. The fundamental had one node right in the center. Okay? Those are odd modes. This next one up is an even node that should have two nodes. Do you see the nodes?
Yeah.
Yeah, they're quasi-nodes, right? This is actually nice, isn't it? This is kind of nice. I don't know if this is old, and I don't know if Pasco makes it anymore. They probably do. It's from Pasco. Okay, what about the next one up? Now we're back to an odd mode again. So we're going to have one node. All the odd nodes are going to have a node in the center, and we're going to have nodes on either side. And now we're back to out of phase, right? So I'm going to do this at, whoa. Okay, so there should be a node in the center there. And then over there you'll see, yeah, it's not bad. It's nice. Yeah, we should get more use out of this. And nobody seems to know about it. I guess that's my fault. Okay, so some terminology here. Again, I keep pounding it into you. Fundamental mode, that's the lowest mode of the system. Very common language. Usually it's more important than the other modes, right? And it has a frequency, F1, some fundamental frequency. And in this case, and it's also true for free, but not free-fixed. It's different when you mix the boundary conditions. The higher modes are just harmonics. 2, 3, etc. The frequency is just an integer multiple of the fundamental frequency. So people call they're sometimes called higher harmonics or just harmonics. Some people call them overtones. We're not going to do that. It's a sort of a musical terminology, and there can be a distinction between harmonics and overtones. We're not going to go there. Okay, so it's not really important for us. The terminology here is a little confusing, as you can see. The first overtone is the second harmonic. The fundamental is the first harmonic. That's what people call it. So you can see that it's easy to get confused here when you want to talk to people about this. You don't want to have to struggle with just the words. So most physicists, the people I know, physicists, they usually just call it the first, second, third mode, right? This is the first mode. That's the second mode. That's a safe thing to do. Okay, any questions so far? Okay, so now, here's the thing about the normal modes. In this system here, or equivalently the pendulum, I better bring this down. Get this out of the way. To represent the most general motion here, you need to add the two normal modes together. We saw how that came about in explaining the beating. In that case, we had an equal amplitude superposition of the two modes. Well, the same thing happens here. We need to consider, we need to take a general sum. It's infiniteness for a continuum with infinite number of degrees of freedom. We have to take this sum out to, in general, out to infinity here. We're adding up all the possible normal modes, which are just the standing wave modes. And each of them has their own pair of coefficients, right? And they have their own frequency. For a fixed string, these are just going to be harmonics of the fundamental. Now, this is going to start looking more and more like Fourier series to you. All right? And it is, but it's different than the temporal or the time Fourier series. You're going to quickly see that, you're going to see, or maybe you're already seeing it, that what's happening in time when we were describing a signal, a periodic signal in time, by thinking of it as a superposition of definite frequencies. Here, it's happening in space, okay? So it is similar to Fourier analysis, very similar, but it's not identical. And one of the ways it's not identical is, look at our modes here. When we did Fourier series in time, we had a fundamental frequency, right? And what was the next? That was the lowest frequency of the content of the signal, right? The period corresponding to the period of the signal. What was the next Fourier component? What was its frequency? Harmonic, twice the frequency. Do you look at this?
That's a bad example.
That's a bad example, thank you. Look at this. Okay, let's see. Okay, I guess I guess the way to say it is this. We had, this actually didn't contribute. We had to have one cycle. Our lowest Fourier component was one period, okay? So there is we would have to start here, and the analogous, the corresponding thing would be to start here and then we would be missing half of the modes here. So that's just one, I didn't do that really well, but that's one of the warnings, that it's not identical. What's happening in time before you might think is identical to what's happening in space in here, and it's not identical. There are some differences. I'm going to point out another difference. Let me go ahead and point it out now, since the first one didn't have a lot of impact. I'm going to describe to you how we would find those initial how we would find these amplitudes in terms of the initial conditions, just what we did before. Okay? Before we were given some periodic signal. So it was actually different. We had some periodic signal and we want to be able to find the Fourier components, okay? And we got something that looked a lot like this, but can you see that it's different? Here are the Fourier components in terms of now it's the initial conditions, okay? And also look at this. If we had an analogy, if you look back, we had one of these was a sine, one was a cosine. So it's not identical. There's just a warning there, it's not identical. Most people just keep these separate. So let's go back here. Here's what we need to do. We need to consider a sum, in general, over all possible normal modes, standing waves in our case. And you can see right from here that we have this, here are the possible modes. They're going to look like this, etc. And now, let's implement arbitrary initial conditions. At time t is equal to 0, okay? At time t is equal to 0, this is not going to be here. And the sum collapses, gets halved, half of it only appears. We just get the A coefficients. So this is what we have to satisfy. This is what a condition on these coefficients to meet some arbitrary initial displacement. We also need an arbitrary initial velocity, okay? So that's the time derivative of this. U is the time derivative, and then we set it the time equal to 0. When I differentiate with respect to time, this cosine is going to become a sine. When I evaluate it at 0, it's going to be 0. So now we pick up just the b's here. Okay, we also get an omega by the chain rule. All right, now, how do we determine that this is similar to the Fourier series we did before? How do we determine these A's and B's in terms of some arbitrary initial condition here? We have to get them out of this infinite sum, right? So you know how this works. Look at this one, right? Multiply by the sine of, to be proper, we should do, multiply the left and right side by the sine of, let's call it mx. Okay, not n here, because n is the index we use in the summation here. Multiply by this, and then integrate from x equals 0 to x equals L. What's going to happen? All these infinite terms here will not contribute except for the mth one. If you don't believe that, sit down and do it. It's very instructive. We're utilizing the fact that these functions are actually orthogonal. They're perpendicular in a sense. And we just took an inner product. Remember I talked about that? If you don't, this is a really important concept in applied mathematics, this orthogonality here. It allows us to determine these coefficients. So if I multiply by the sine of kmx, integrate, when k is equal to m, I'm just going to get the sine squared. It's not going to be 0, and it's going to give us a factor of 1/2, so we can find this. When m does not equal n, the integration is 0. There's no average overlap there. It's like they're 90 degrees, they're orthogonal. So we talked about that before, and if you don't believe it, it's really worthwhile to sit down and do it, to believe it. It's a very powerful tool, this orthogonality idea. So we've got the A. Here it is. Now, now, everybody does this, okay? Now when you're done, you replace m with n. But unfortunately, we had to do that because we were using the n here. And here's what you get. That's going to look very familiar. It's very similar to the time series. But it's, again, there's this difference here. In the time case, we had a sine and a cosine here. Remember that? I don't know if you remember that. But now, so you want to be careful. We have to have a sine here because these are the standing waves. They go like sines for fixed string. We do the same thing over here. Same trick, orthogonality trick. And you get this. Now, notice I wrote something in here later, the red here. We have found, in general, it may be trouble doing this integral. You might have to put it on a computer. But the point here is, we have found these coefficients in this infinite expansion here for any initial conditions. That means that these functions here that we're using are complete. And that's just, I may not have used this word before. It means we have the general solution. When you have a complete set of functions, that means you can represent any function as a sum of those functions. So mathematicians often use the word complete. It's a lot shorter than saying, the general solution. So we actually proved it in this case. Suppose we have this infinite superposition here. We can find the coefficients in principle for any initial conditions. Okay, any questions? So we're going to do an example. This is going to look, it's going to be familiar to you when we did the time series, but it's, but again, there's a distinction between the two. So we're going to do what's called a pluck string. And we talked a little bit about this in the past. A pluck string is where you pull, a normal pluck string, you pull this up like this and let it go from rest. Now I need to point something out. That this is not the quiz problem, right? What's the quiz problem? One of the problems on the quiz. It's plucked in a strange way. It goes down to here. Somebody has actually held, it'd be hard to do. It'd be kind of hard to do. But somebody has fixed it equally on either side here and then pulled it back like that. Because the initial disturbance, and that's a legitimate initial disturbance. So it actually looks like this. So it's initially at rest, okay? But this is different. This is, and what you can imagine is somebody who's, you've held those down and all those 3 points have been released at the same time, okay? But I don't want you doing a normal mode analysis for this. This is a pulse problem. That's a pulse problem. And we hadn't talked about normal modes before that, okay? So you want to think how you would imagine getting this situation by superposing a right traveling pulse and a left traveling pulse. It's a different problem here. We're going to find solve for all the modes, the modal content of this initial plucking here. How do we describe this, the function here initially? Remember, it's at rest, so the u at time t is equal to 0, there's no velocity. And this is just a straight line, so we can, it has to end up being at height h here after distance L over 2. So it's proportional to x, and this is the coefficient you have to have, so that you end up there in terms of h. And here it's going to now start, at this point, x equals L over 2, it starts and has negative slope. You can show that it's described by that. We don't really need to worry about this. We have symmetry. So in our integration here, we're not going to integrate over this. We're going to integrate over here and double it, right? As you've seen before in the time series. Okay, well, what are the b's? All of the b's have to be 0. Because there's a u of 0 here, and u is the 0 velocity everywhere. So all of the b's are 0. What about the a's? Here's the first a here is the fundamental. So you can see that the fundamental, which is half of a sine wave here, it's a crude approximation to our initial condition. So in our superposition of modes here, it's going to contribute. What about the next one up? The next one up is a wavelength here. It has a node there. So it looks like this. The second harmonic looks like that. Is that going to contribute to our expansion here? No, it cannot. Because it has the wrong symmetry, right? It doesn't help us reproduce this. And if you don't believe it, just like the Fourier series before, you can plug it into here, okay? In fact, we can do it right now in our heads. The second mode looks like this, right? It has a node there. It looks like this. So, and here's our function, yx of 0. You can see that about this line right here, I have positive contribution. When I multiply the two functions, it's positive here. It's equally negative over here. So it's going to vanish when you do the integral. And you can explicitly do that if you really want to. And some of you have done it, I notice. Remember, I'm the one who grades the quizzes, right? We don't have any TAs here. So you can do it, okay? But it should be clear to you now, and I know a lot of you have the concept. I can tell by grading the quizzes. So all we're going to get are, in this particular case, it's not true in general, in this particular case, we don't have any of these because we have initial velocity 0, and we're only going to get the odd coefficients. Only the odd coefficients will contribute, or the odd modes, the first, third, fifth, etc. So the way we say this in acoustics is, when you pluck the string, you do not excite those modes. We have a real physical way of looking at it. And it's important because, for example, musical instruments, you take a guitar or something and you pluck it in the middle, half of the modes you're not exciting. And you can hear the difference. If you pluck the string near the bridge, okay? Let's say this is a guitar string. And here the tuner's over there. If you pluck it here, you can tell there's a difference in the tone. Here you're exciting many more modes. Not all of them, okay? Because there's going to be a mode that has, it depends on where you pluck it here, but eventually if you go high enough, there'll be a mode that has a node right where you're plugging. You're not going to excite that mode, but that is typically way up there the closer you get to the bridge here and pluck it, the more modes you're going to excite. So people just naturally do this when they play guitar. You know, if you can be taught this, but let's face it, there are a lot of guitar players out there that are self-taught, right? Guitar is a popular instrument, I think.
Yes.
Okay, thank you. So you just get a different tone, and you're exciting more modes. And here it's actually it's a different effect, and usually considered somewhat boring when you pluck it right in the center here. Okay, well, let's solve for this. Okay, so here's the form. This is the Fourier type formula that's gotten from the orthogonality of the modes. I've substituted, well, look at this. I don't know if I made a statement about this, but when the notes are typed, there'll be a statement in there, I promise you. we're integrating by symmetry here. All we have to do is integrate, as I said before, from 0 to L over 2 and just double the result. So you see that 4 there in our basic formula, we have a 2. I've doubled the result due to the symmetry here. It's clear. We're going to get the same there as for the fundamental and for all of the odd modes. So I've done that. And now here we go again. And I know some of you are weak on this, but it's worth paying a little bit of attention to it because it's really not a mystery. We're going to have to integrate by parts here. And you can make life easier on yourself, and you're less likely to make a mistake if you define a new variable for the sign here, because this stuff just gets in the way, makes it more complicated. So I'm going to call all of this something, W. And I'm doing that to make this simple. Then I have to pay a little bit of a price here. I've got to convert. I can solve this for x and substitute the result in here. And I got to do the same thing for dx too, because I got to put everything in terms of w here. And incidentally, the upper integral, you have to transform that to w too. So it takes, you're putting in effort on the front end here, but in the end, you're less likely to make a mistake. Now we have a classic integration, simple integration by parts problem. Here's the antiderivative, or the integral, also known as the integral. And something's bothering me here. This is not, something's not right here. I think I've done 2 steps. Sorry about this. Looks like I've done 2 steps. When we integrate by parts, we shift the integral. Yeah, I think I've quoted the result here. I haven't actually gone through. This is what you get if you looked this integral up. Okay? That's the best way to see it. If you look it up, this is what you're going to get. I've skipped, if you want to go through the integration by parts, you replace this integral with an integral of where you shift the differential from here to there. You shift the differential from here to just a dw, and it becomes an integral that's easy to do. So I've actually skipped that part. But anyway, so this is what you get if you look it up. And now we carefully evaluate it here. And when you go through, you'll see here that at n pi over 2, the cosine is going to be 0. The upper limit will be 0 here. All right? And the lower limit will be what? 0, because we have a 0 there. Over here, we pick up the sine of n pi over 2. That's not going to be 0. And in fact, at 90 degrees, or pi over, let's go radians here. At pi over 2, it's going to be 1. At 3 pi over 2, it's going to be minus 1. So it goes back and forth. So you can represent it as minus 1 to the n minus 1. But now for an important point that many people did not do on the quiz, on this, for a time series problem, a Fourier time series problem. When n is odd, what is this? You don't want to leave it like this. What is it? It's 1. When n is odd, right? So you don't have to deal, because we only have odd coefficients, the only non-zero coefficients are odd, we can simply replace this. It's much simpler. So you want to do that. Don't leave something like this. You only leave it when n is not specified. But if n is odd, or n is always odd or always even, you can replace it in a simpler expression, plus or minus 1. So here's what you get. This is suspiciously like the triangle wave that in the quiz. Okay, I think it might be identical, but I don't encourage you to try to make a connection there. It's best just to stay away from that. Okay? But I think it looks very familiar to me. So now, having determined the coefficients, now we can go back to our general expansion here and substitute the expressions in. And in unusual situations, you can actually do the sum. Okay? If you really want to. And let's see, I hadn't thought of it until right now. Forget it. I really doubt that you can do this sum analytically. It just doesn't look good at all. So forget I said that. It's probably not in acoustics like this, situations like this, like with a string, probably never happens. But it's conceivable, okay, that you could actually do it. I don't see how here. Okay, one final question. Everybody okay? So this is how we now have a solution to our problem. A unique solution for the specified initial conditions of a plucked string. Other examples, as we mentioned before weeks ago, is you could have a hammered string, like on a piano. Okay. There we have an initial displacement of 0, but we have a non-zero initial velocity. Same idea mathematically going through this. Now there's an interesting question here. Does this motion repeat? Does the motion repeat? You got all these modes here. Well, the key is, remember, they're all harmonics each other. So if you have a period, look at the fundamental is going to have a certain period. I'm calling it capital T here. It's 2 pi over omega 1. That's the period of the fundamental. So the fundamental will repeat. The fundamental mode, n equals 1, will repeat after this time. What has the second mode done in that amount of time? It's gone through 2 cycles, so it repeats too. What about the third mode? It's gone through 3 cycles. So it's a very simple explanation. Here's the math. It looks kind of complicated. If you advance the time by a period t, you'll see that all these cosine omega t's, they get advanced by this amount. But when you simplify, you never want to leave omega and t. Some of you have done this in quizzes. You can simplify this. Here's omega n. There's the time that we're considering, the fundamental period. And you can see that it's 2 pi n. I'm going to get the cosine of at some time advanced by 2 pi n is the same if I don't have the 2 pi n there, because this is just a multiple of 2 pi radians. So this tells us that the motion repeats. And again, the simplest way of seeing this is, after a period of the fundamental, the fundamental is repeated, the second mode has gone through 2 cycles, the third mode has gone through 3. It's as simple as that. It's got to repeat. The motion has to repeat. Now I want to point out that that's without damping, right? What do you think is going to happen? And unfortunately, we're not going to do that in this course, but next course we will. We will look at damping of acoustic modes. In open space and in a tube. What do you think is going to happen? Do all the amplitudes go down the same? Do they all exponentially attenuate? Where's our solution here? Do I just put in an e to the minus beta t here? I could, that's a model, but what do you think happens? What's your experience? You've all probably seen this kind of thing happen before.
Higher frequencies attenuate first.
Faster.
Faster.
Yeah, right. That's almost always the case. So what's going to happen here is the motion, first of all, the motion will not repeat. Also, it will sound different to you. It'll sound different to you. So it's going to sound more and more like a pure tone, just a boring sort of pure tone, like from a tuning fork. Tuning forks, did I tell you guys about tuning forks? Did I mention this? A tuning fork, this is the fundamental mode. There's the next mode up, kind of looks like this. Did we talk about that? It turns out, because of the geometry, it's way up there. It's like 5 or 6 times, I can't remember, roughly 5 or 6 times this frequency. So it's a lot higher frequency, and consequently it damps out very quickly, and you get this nice pure tone, which is what you want for a tuning fork, I think, right? Even though nobody uses them anymore. Okay, any quick questions? Okay, so tomorrow I think it's problems, right? And then you know what that means.